started. Good morning, everybody. My name is Holub. I will be giving this talk and a few others in this session or in the conference. I'm also going to be around all week, so if you have any questions and want to come up to me and ask them, feel free to do that, please. By way of background, for those of you that weren't in my session yesterday, is that it's kind of an exception for me to be doing these talks about specific technologies. Is that usually what I do is Agile-related work, and most of the actual consulting work that I've been doing lately has been involved with either training in Agile or getting people up to speed in Agile, moving a company in the Agile direction if we're not there already. But I also work on a lot of startups. In fact, I'm working on 2 startups simultaneously right now, which is something of an experience, though not a lucrative one. And I don't know if you've ever worked at that level, but basically, when you're the CTO of a startup, that means you're the programmer. And so in the process of doing that, I'm putting together a couple of systems that involve a lot of interesting technology, which is mostly what I'm going to be talking about with the technology talks today. Is I use Rabbit a lot. I'm a huge fan of messaging in general. And of Rabbit in particular, I've used several messaging infrastructures, and Rabbit is the one that I am the happiest with at present. It's likely to change a week from now, but at the moment it's the one that I'm using. So my plan then is to talk about Rabbit itself and about messaging in general. I'm going to spend this is the first time I've done this specific variant of this class, so I might have more slides than we'll actually have time for. I want to spend most of the time it's sort of at the core of the class, talking about topologies, talking about how to organize messaging infrastructures for doing specific things. And that's the critical thing to talk about. Towards the end of the session, I'm going to go through a lot of code examples. But those are mostly minor variants on the examples that are parts of the tutorials on the Rabbit website. And I can add some value to that by explaining things that aren't explained well in the tutorial, but if we run out of time, you can just continue with the tutorial and that'll be fine. I think we'll have time to cover everything. It's not that hard to program. The other issue with these particular slides got to the conference a little late, so I put them up on my website. If you want to download them from the website, feel free. Is that the ones on the conference site are a little bit stale already.
Is your microphone enabled?
Oh, good question. No, it's not. Thank you. I won't repeat everything that I just said. The camera is just going to have to deal with the fact that nobody who's watching the video will know who I am. Go look me up on my website, then hire me. But anyway, the slides are up on the website. I leave them up there more or less permanently, though as I update them for other conferences, they update on the website too. The current version is the current conference, so they'll be the same. So let's talk a little bit about messaging. Is the whole point of a messaging system is to decouple the pieces of a larger system. And decoupling is a particularly important thing that people don't talk about for a lot of reasons. Or don't know about for a lot of reasons. I don't think about it for a lot of reasons. But with all of the systems that I work on, at least, if for no other reason, you've got to be thinking about scalability. I'm going to do a talk later this afternoon on cloud infrastructures. And most of the, in fact, all of the sites that I've been working on for the last couple of years have been hosted in the Amazon cloud, in the Amazon EC2 service. The thing that makes Amazon interesting is that as the load on your website increases, you can throw more processors at it. You can spin up additional virtual machines and hook them into the system and get them to work. Messaging is a huge part of being able to do that, because with messaging you can bring a new machine online completely transparently to the rest of the system while it's running. And the system then automatically takes advantage of the new resources without you having to do anything. It just scales automatically. So from an architectural point of view, messaging is extremely important from a scaling point of view. It means that you can have a load balancer that is monitoring activity on the site, and when it sees it get above some threshold, it introduces a few more virtual machines, all of which are running some piece of the messaging system, and which can then do work that they wouldn't otherwise be doing. There are other important reasons with respect to modularity. It's very easy if you're using messaging, for example, to replace a module with a replacement hot. In other words, while the application is running, you can replace an old version of something with a new version of the same thing without having to bring the application down. And zero downtime is extremely important in a website, obviously. Because you have no idea, it's running 24 hours a day, basically. There's no off time. There's no convenient time where you can bring the site down for 10 minutes and put up some idiot screen that says, I'm sorry, but the system is under maintenance. If you ever see one of that, that's a clue that whoever wrote the site didn't know what they were doing. So messaging is what makes that possible, because with messaging, you can take a module and you can bring up the new version of the module and have the old version and the new version running in parallel, and then bring down the old version and effectively replacing it with the new version. Again, all completely transparently while the system is operating. So messaging, and there's a few other issues too associated with messaging. There's another slide that's coming up in a few slides, but I'll talk about it now just because I'm on the subject. Is in the Agile world, where I work most of my time, messaging is also essential because when you're talking about a system that's made up of independent units that are using messaging to talk to each other rather than a direct network connection or something along those lines, then from an Agile point of view, that gives you many choices that you wouldn't otherwise have, because the things at either end, the producer and the consumer that are either end of that connection, can be written in any language, running on any machine that runs any operating system. So what that means is that you can have these heterogeneous systems where the pieces look completely separate from each other. One of them is running Ruby, one of them is running Java, one of them is running C#, and even running different operating systems. So the C# version is running under a Microsoft operating system, and the Ruby version is running under Linux, and it all just works, as everything fits together nicely. And if you decide to make changes in the languages that you're using, again, everything just works. So from an Agile point of view, that's essential, is that as the systems get larger and larger and larger in an Agile world, you need to be able to customize the implementation for agility. And the fact is, there is no one programming language that's good at everything. I wish there was, but there isn't. So it is often the case that you want to write part of the system in one language, in one environment, in one operating system. You want to write a different part of your system in a completely different language, in a completely different operating environment. Messaging makes that possible. Not only possible, but it makes it easy. We'll see when I get to the code examples that Rabbit has a lot of inter-language facilities. So the Rabbit clients are written in about 8 different languages officially, and you can get more language support online from the user community. So pretty much whatever you're working in, you can connect to Rabbit. So messaging solves many, many problems. The basic idea is what we're seeing on the slide in front of us, is that you have a producer of messages, a consumer of messages, and a broker in the middle. Rabbit is the broker. Typically, these are going to be running on 3 separate machines. They don't have to be running on 3 separate machines. The broker could be a single computer. It could be a cluster of computers that are acting as one large computer. It could be a cluster of computers that's acting in a looser kind of way. So a message can be sent to one of the machines in the cluster, and then it will relay it to another machine in the cluster where it gets picked up by the consumer. So all of these are possibilities. These big messaging systems might be running 7 or 8 CPUs simultaneously in a cluster in order to handle the load. The processing of the message is reliable. In other words, the message here contains a couple of things, right? Is that the message itself is what I'm thinking of as the envelope. And that contains a payload, which is really just a binary blob. It can be anything that you want. The message itself, just like an envelope, has certain information associated with it. There's probably 30 or so headers that are part of the message itself, 4 of which you'll actually use. But effectively, it has addressing information in it, which is the important thing. So the payload doesn't have any knowledge about the addressing. It doesn't really know where it's going. The message then moves through the broker across to the consumer. So the broker is in the middle of everything, and the broker is making sure that the delivery is relatively reliable. Is that Rabbit is pretty good about that. There are some systems that are rock solid good at reliability. These are called guaranteed delivery systems, where if you send a message, it is guaranteed that will arrive. If the consumer goes offline for a year and then comes back online, it will then receive the message. Rabbit is 99.99% of the way there. Is that it's quite reliable. There are a couple of use cases that are well documented about that tell you situations where a message might not arrive. But in Rabbit, you can always tell that the message didn't arrive. So though you don't have a guarantee of arrival, you do have a guarantee of at least knowing. So you can send the message again if you need to. And for my uses, that's good enough. I've never had a problem with reliability with respect to the message transport. So getting back to the sorts of things that I was talking about earlier is that we're accommodating new requirements relatively easily because we can change any of the components. We can change the producer, we can change the consumer, we can reconfigure the broker if we need to. But that's a relatively rare occurrence. Hot updates, we can unplug a consumer and plug a new consumer in. There can be multiple consumers connected to the broker. We didn't see that in the last slide, but we will in a moment. So you can run them in parallel. Messaging is really good for doing background processing. You can have a web server as a producer, and the consumer of the message could be something that's doing some slow operation in the background. So you can take operations like sending email or doing some kind of image manipulation or some kind of rendering operation and pull it off your web server and move it to a secondary server, which you're talking to through the messaging system. And that way the web server can be much more responsive and you don't have to worry about overloading your front end. Is that most websites fail when web servers fail. So this is a way of putting easy background processing into the system. You can distribute your development really easily. Is that I've worked on several systems where we were scattered across a geographic area, and the running system was held together with the messaging infrastructure. And we were actually using local machines for deploying our part of the system, which was then integrating to the system as a whole across the messaging infrastructure. Is everyone understanding what I'm trying to describe there in terms of topology? So I was in California, and I had my messaging, it was both a producer and a consumer, but it was outside the broker. And then one of the people that I was working with was across the bay in San Francisco, and one of the other people I was working with was in Southern California down in San Diego, and then I was working with a guy in New York. And we had a broker set up, and each of us had our systems connected to that broker, so we could do hot updates on the system. And the system itself was geographically distributed so that we each had a server in our own location so we could mess around with the servers. That was pretty valuable, and again, I don't know how we would have done that without some kind of messaging infrastructure. Different languages I talked about, and different operating environments too, of course. Sharing information is messaging is extremely good for sharing information. And right now, a lot of websites that I see that are badly done use the database for this purpose. Is that one server will put information into the database that another server will pull out. You see this a lot with session information, for example, but you see it with other parts of the program as well. That's almost always a disaster. It's slow. More to the point, it's using a database resource for something that really doesn't have much to do with the long-term storage of data. It's just using a database as a convenient way to move information around. And that's not actually a good use of a database. Because messaging is a better use. It's more efficient, and it's more scalable, and more to the point, it frees the database up to be a database. Is that you're not wasting all these database connections, just using it as a blob for storing data remotely. The most important one, though, is that it makes your development go faster, because everybody is working on independent pieces. So you're not stepping on each other's toes all the time as you're doing development. You can also experiment much more easily in this kind of environment. Again, if you're using messaging to communicate to another module, if somebody wants to just experiment around in that module, say, well, let's rewrite this in Python. Well, you can do that without impacting the rest of the development team. And that's an important ability to have, is that it makes development go faster generally. And of course, it improves the flexibility of the system for the same reason. The final one, which is the most important one, though, is it helps you get the product out the door faster. For all of the reasons that we've been talking about. And in an agile world, that's particularly important, is that you're releasing every couple of weeks, and nothing can get in the way of that 2-week release cycle. So being able to get something out the door that's valuable every 2 weeks is important. And all of the things that messaging gives you, particularly the separation between modules, makes it much easier to get that product out the door, because you can be working in one corner of the system and just not have to worry about what's happening elsewhere. So Rabbit itself is supported on a bunch of operating systems. I've listed most of the big ones here. Pretty much anything that you'd be interested in. Oh, also Windows. Oh, there's Windows in the corner. I mean, I still don't recognize the new Windows logo. I updated all my slides when they changed the logo, and now I don't recognize it on any of my slides. But it supports IIS and all of the kind of standard Windows implementations that are used in the server. But pretty much every known version of Red Hat is supported, or of Linux is supported. I've said Red Hat. That of course means that it also supports CentOS, which is the open source public domain version of Red Hat. So it runs on basically everything. Rabbit itself is written in a language called Erlang, which I have mixed feelings about. Erlang is a bizarre language. I don't recommend that anybody on the planet write something in Erlang, which is a deviation from most people who talk about Rabbit. If you go online and you look up RabbitMQ and find some talks on it, they're always written by guys that are working on the RabbitMQ project, and they spend the first half of their talk trying to convince you to do all your programming in Erlang. And just ignore that. I would never do it. Erlang is a weird language. It's based on Prolog as its syntax, and nobody knows Prolog, so nothing is familiar looking when you look at the program. It becomes a write-only language. It is a functional language in the strict sense of the word, which is to say that there are no variables in the language. In order to do the equivalent of assigning a variable, basically you're replacing the variable with something that has a new value in it. C# and Java both do this with strings, for example. You can't modify a string. You can only get a new string that has the new value in it. And Erlang, the entire language is like that. Now, you'd think that would be inefficient, but what it does give you is something that is actually important in a messaging implementation, which is thread safety. Is messaging implementations, message brokers are hugely multi-threaded. And Erlang helps a lot in that kind of environment because it gives you a reliable way to do multi-threading without any of the problems that are typically associated with multi-threaded systems. So Erlang is almost perfect for implementing a messaging infrastructure, implementing a broker. But that's probably the only application that I would recommend using Erlang for. And since the Rabbit guys have already done it, we don't have to do it ourselves. We don't really care that it's implemented in Erlang, except in order to run Rabbit, you have to be able to run an Erlang virtual machine on whatever development platform, whatever deployment platform you're working on. The Erlang virtual machine is not quite as good as either the CLR or the Java VM. So it's not quite as fast. And that's the one downside in terms of the implementation, is that the broker could run a little bit faster than it actually does run if it had a better virtual machine underneath it, but we're kind of stuck with the Erlang virtual machine. On the other hand, as I said earlier, it does cluster really well, so scaling up the broker by adding more machines is not just possible, it's relatively easy. It's a polyglot language in the sense that there are many, many implementations. Java, C#, Erlang, Ruby, and Python are the native ones. Or put it another way, these are the ones that are actually supported by the Rabbit team. The other languages on this list are supported by people in the user community, including COBOL. There is a COBOL port of the Rabbit. People laugh, but actually messaging infrastructure is used extensively inside extremely large enterprise applications that have a lot of legacy code. Messaging is a way of taking a chunk of legacy code that was not written to work on a large network, and nonetheless get it to work on a large network. So COBOL interoperability is actually important. Is that there are many corporations that still have active COBOL code bases for some parts of their system, and if it weren't for messaging infrastructure, you could not use those COBOL pieces anymore. So pretty much any language that you can think of that you'll be able to get support for. The other interesting thing about Rabbit, which is extremely important, is that it supports everything using a standard messaging protocol. And which is to say other messaging systems support the same protocol. So a Rabbit cluster can actually send messages to a different messaging system entirely, something that's got no connection with Rabbit, that supports the same messaging protocol. So that means that you can hook together two systems that were independent and are actually using independent messaging, but once you hook them together, it's as if it's one large messaging infrastructure, because the messages can move from broker to broker. Right, that protocol is AMPQ. That's the main one that people are using now. It's an open source protocol It was developed by, it's binary, right? It's a wire level protocol. In other words, it's controlling what's actually happening on the wireless. These things move across the network, which was what makes the interoperability possible. It was, I don't know if I said this in the slide. Obviously it's efficient. That's important also, is that the standard was actually put together by people who are users of messaging systems. It's one of the few standards that I actually like for that reason. It's not a bunch of academics. There were a bunch of people that were messaging infrastructure companies that were participating in putting the standard together, but there were also many, many, many just normal users who were putting it together. So it actually does everything that it needs to do, and it does it pretty elegantly. So it's a good standard. Phones, I'm not going to talk too much about phones, but there are messaging clients that actually will run on cell phones too. So your messaging infrastructure can actually extend the messaging cluster from the cell phone. And you can use messaging as a means of communicating from a cell phone to a server when you're building web applications. That's important. Right? The protocols that do that typically are on top of HTTP for obvious reasons. Right? So they're not strict messaging, but it's pretty close. So let us look at a couple of common situations. The most important one is the simplest one, is that you have a message which is going from a producer over to a consumer, which then replies with another message. Now I should say that it's also possible to reply with the same messages, that I changed color to demonstrate that you can reply with a different one. But bear in mind then, we'll look at RPC use cases in a minute, remote procedure call use cases in a minute. But bear in mind that if you're going to do something like a return value in a messaging system, the way that you do that is by sending a message that has a return value. So does everyone hear what I'm saying here? Well, if you're thinking about a remote procedure call kind of application for messaging, where if you think about a REST protocol, that's a pretty good analogy, right? So you're making what amounts to a function call on another server. The way you do that is you send a message. And the message will contain typically a bunch of JSON, is what people use mostly nowadays, because everybody's using JSON for everything. And the first field in the JSON object will be the name of the method that you want to call, and the other fields in the JSON object will be the arguments. And that's received by our consumer, who then does whatever operation was requested. But if that consumer needs to issue a return value, the way it does it is by sending a message back to the sender. Right, so there will be two messages involved. As the message typically does, it's not a single message making a round trip typically. It is rather one message being sent to the consumer, who then sends another message back to the producer, which in this case becomes a consumer, right? As you're flipping the chart over. And we'll look at an example of that if we have time later on in the session. The message goes to a consumer, but there's no requirement that it go back to the producer. It could go down to another consumer. You could relay it through a system. And that's particularly valuable for getting some piece of information distributed to multiple systems. And in fact, that can keep going. You can keep bouncing around inside the broker as much as you want. By the same token, a message can leave the producer and then simultaneously go to multiple consumers. And that's particularly important for a lot of applications, particularly logging applications. In other words, you can have multiple log receivers. The consumers are receiving logging messages. And you can tune them at certain levels. So you could have one consumer that's receiving all log messages associated with a given server, a second consumer that's receiving only those log messages that are associated with a given application running on a given server, a third receiver that's receiving log messages for particular RPC calls within a particular application that's running on a particular server, so you can fine-tune things. But more to the point, the fact that you can receive stuff the multiple consumers can receive stuff, again, makes it possible to get reliability in a large web application, because you can have processing going on in parallel between multiple consumers and just throw away the results of one of them if you need to. If you need absolute reliability, in other words, this is a way to get parallelism into your system where the same request is being simultaneously executed by multiple machines. And then you use the result that is arbitrarily the one you happen to use. But more to the point, if a machine goes down halfway through the operation, the second machine is halfway through the operation and it completes. So it's a way to get reliability into systems that have to have very high reliability. Right? Is everyone with me here? I know it's early in the morning, but when everyone is this quiet, I will start getting nervous. So I like questions. Yeah.
Can the broker also keep track of a consumer that is doing work?
Yeah, the broker keeps track of everything. So there are logs associated with the broker that show you all of the message flow through the system. And more importantly, when we get into topology in a moment, these consumers are actually a little more complicated than this. There are things called exchanges and things called queues that are in the system. And the broker can tell you what the status of all the exchanges and queues are. So you can look and see where things are stuck. You can see there's a message sitting in this queue and it shouldn't be. So why is it still there? Is who was supposed to pull it off the queue that didn't pull it off?
And if one consumer is doing work, you could send it to an idle queue.
I didn't hear you.
If one consumer is doing work, you could send it to an idle consumer.
Yeah, and we'll also see in a moment that there's sort of a poor man's load balancing that goes on in here. In that the messages come round robin amongst consumers, for example. Now, in terms of general topology, under the covers, we have a situation that looks something like this. And I'm going to come back to this topology information more later on in the talk. As I said a moment ago, the most important thing that I can cover is topology. Is that when we start going through the code, that's interesting, but you can get that by just going through the tutorials. You don't need to be in here. The basic idea of the AMP, this is all really mandated by the AMPQ protocol, so pretty much everything that does AMPQ is going to do this. You have producers, those are the blue circles with the P's in them. You have consumers, which are the blue circles with the C's in them, obviously. In the middle, you have two classes of objects. You have exchanges, the green X's, and you have queues, which are in red here. Queues are effectively infinite length, first in, first out message flows. So they can hold, they say infinite, I assume that there are practical limitations based on the size of your hard disk, but hard disks are very large nowadays. You can hold an awful lot of messages on your average 18 terabyte hard disk, right? So it's not a, they're effectively infinitely large. So you don't have to worry about sizes. You just think, I want a queue here, and you don't worry about sizes. The exchanges are routing systems. So queues don't know anything really about routing. Is that a queue really is just a queue as messages come in one end and go out. So in order to get a message into a queue, you have to have some way to route it there, and that's what the exchange is going to be. Now when we start looking at the examples, there are a few of the examples won't have apparent exchanges in them, so that you won't see anything that looks like an exchange, and that's because there's always going to be at least one default exchange in the messaging system. Typically it has no names. Exchanges, all of the things here, the queues and the exchanges can all be named. They don't have to be, but they can be. And there's always going to be one exchange that's not named that's used by default if you don't specify an exchange. And what that exchange does is it routes all messages that it gets to all queues. So it's a cheap way to do simple things. Let's put it that way. But if you're doing anything that's not just dead simple, you're going to have to start building your own exchanges also. All right. Exchanges can talk to each other. I haven't shown that here actually in this picture. There should be an arrow between those two green boxes to demonstrate that exchanges can talk to each other. So you can relay a message from one exchange to another exchange in order to do some sort of complicated routing. Exchanges can talk to as many queues as you want them to. Queues can be hooked up to multiple exchanges, so they're receiving messages from multiple places. But notice that there are no lines between queues and queues because in order to do routing, you have to go through an exchange. When the messages arrive in the queue, so they can go out to the consumers, and you can have multiple consumers attached to a given queue. In Rabbit, if there are multiple consumers on a queue, then the messages that arrive at the queue will round robin between the consumers. First consumer will get one, the next consumer will get the next one. You can override that if you want to so that it broadcasts out, but that's not the standard. That's not standard. It's typically the way if you're going to do broadcasting, you'll do the broadcasting in the exchange and then have multiple queues with one consumer on each queue. All right, is everyone over here? Now the final part of the mix is this notion of a binding. The bindings contain routing information. Bindings all are labeled, and the label is important. So the basic notion of a binding then is that it is it holds part of what amounts to the address of the consumer. And we'll see how that works again live in a moment. But the basic idea of bindings is that the sum of the labels on the bindings is how you control the route from the producer to the consumer. So routing is actually a relatively complicated thing because it's a combination of what the exchanges are doing and what the bindings are doing. The bindings control what exchange you go to. The exchange then controls some kind of outbound multiplexing, some kind of outbound routing. And then the bindings on the outbound side of the exchange also control whether the message is going to go to a specific queue or not. So is everyone following me here? So queues are named. I guess this is the important lesson, is that you conceptually you're thinking about, you don't think about exchanges. Conceptually you think there's a producer and it puts a message on a queue and a consumer pulls it off. And what that does is it makes you think the queue has an address. And that's not literally true. What has an address is the route to the queue. Is everyone understanding that distinction? It's important. Again, I'll look at a couple of examples. So this architecture gives us a couple of good advantages. It gives us decoupling. In fact, it gives us 3 kinds of decoupling, all of which are important. Logical decoupling in the sense that the producer and consumer don't know that they exist. I can send a message off into the cloud thinking some consumer will pick this up, I don't care who. So they're completely decoupled. Physical decoupling means that there are different locations. They're at the producer and the consumer are actually on different machines in different parts of the country or in different countries. And then temporal location in the sense that you send a message off and it gets service eventually. And we don't really care when it gets serviced as long as it gets serviced eventually. Databases are starting to leverage this kind of notion, this notion of eventual consistency in databases, which is a similar kind of concept with respect to messaging. So for logging, for example, you don't really care when the logging message gets serviced as long as it gets serviced.
I have a question. Where is the broker located? Is it running on the same?
It can be on the same machine as the queues, but it doesn't have to be. The queues are effectively in the broker. So the broker is not, but the producer and the consumer and the broker could be all on the same machine. When I'm building a system and testing, it is all the same. So it is all the same machine.
It's a separate process, though.
Well, it could be. In other words, a broker is identified by its IP address, its location in the network, and you can use localhost as the IP address, but it could also be the address of some machine somewhere else on your network, or it could be an address of some machine somewhere else on the internet. It doesn't have to be local, but it can be.
So when you use it, even in simple situations where you have one type of client and one server, for instance.
I do all the time.
You still use it.
Yes.
So the broker would sit on the server.
Would sit on the same server that the web server would sit on the web server. Yeah.
Does it complicate deployment or?
Slightly, right? As you do have to launch the broker, right? But that's just one line of code, right? It's a broker, you just execute it. Just a program that you put it in the background and you're done. The brokers all have remote control panels of one sort or another associated with them. Rabbit has a reasonably good remote panel that works over the web, has a web interface that you can use to connect to it. But yeah, it can all be on one machine. And when I test, it's almost always on one machine because I've scaled the system down to fit my testing.
Yeah, do you just have one broker? And if you have one broker, like how scalable is it?
How
scalable?
You have one logical broker, but it can be broken up into many physical machines running instances, so each running its own instance of Rabbit.
Okay, so do the brokers have to communicate with each other then? Or?
Yeah, but you don't think of that as a programmer, you just think of the cluster as being one broker. So from a programming point of view, it's as if you had one broker. But when you configure the system, the broker could be implemented with multiple instances of Rabbit running on multiple machines. But you look at it as one logical broker, so you don't have to worry about that.
So is that how you scale your broker?
Yes. And you can scale the brokers both as a cluster, sort of an anonymous cluster, in the sense that the cluster is one logical broker, but you can also scale it as you have a local broker that you know about that talks to a remote broker that you don't know about, but the consumer over there knows about the remote broker and messages go broker to broker. You can do it either way. I've never actually done that. I've done it as a cluster, but I've never actually done it as remote brokers that communicate with each other. But you can't, Rabbit supports that topology.
So does that slow down your system because you're going to have like much higher latency?
Yeah. You're going to have higher latency if you have multiple brokers, but you'll also have a lot of parallelism, so there's some advantages. Is that you have control over whether the message is durable or not, whether it's actually going to have any real lifetime associated with it, whether you can actually guarantee that it will arrive. The more durable you make the message, the more resources you're going to use in the broker, because you've got to store it on a disk, for example. If the message is transient, you don't need to store it, you can just pass it right through, and then it becomes very efficient. So for logging messages, I don't make them durable, it's not worth it. If I lose a log, I don't care. On the other hand, if it's something important, right, some piece of database information that has to be updated, I'll make it durable, and that way I'll be sure that it will arrive, but it will use more resources in the broker. Yeah. The broker's not doing much though, right? In other words, I think I wouldn't worry too much about overhead in the brokers. It's that I think the overhead is more at the ends than it is really in the middle, is that it's not doing a whole lot. Okay? Now, the queues and exchanges can operate in various modes, or there's various ways of thinking about their modes also. There's a sort of a passive mode where the queue is not actively doing things, is that you have to check it in order to see whether there are things to do on the queue. There's the notion of a durable queue or a durable exchange, which continues to exist across the lifetimes of the brokers. And that's important because if you have a durable exchange and a durable queue, then the broker can crash, and you can restart it and you haven't lost any messages. Of course, if things are durable, they have to be staged to disk, because otherwise you don't get the ability to shut down your broker and bring it back up again. So there's always trade-offs here when you do it, but you have the choice is the important thing. Brokers can be exclusive, or the exchanges and queues can be exclusive. They don't have to be though. In other words, you can set things up so that only one consumer can connect to a given queue, or only one queue can connect to a given exchange, which again gives you some efficiencies in the routing because you don't have to worry about multiple connections instead of one connection. So you have choices over all of that. And then you have auto-delete queues and exchanges, which are queues that are created for one particular purpose, and once that purpose is satisfied, the queue goes away. Remember, the queues are going to exist inside the broker. So if you're doing what's called a publish-subscribe strategy, in the sense that somebody is publishing a bunch of messages out to the broker, and you want to subscribe to the message in the sense that you want to find out when the message has been sent. You can have multiple subscribers to a given message. In other words, one producer produces a message and multiple subscribers receive it. This is really good for event notifications. Sometimes when you get the notification, you're uninterested in other notifications. In other words, you create a queue strictly for the purpose of receiving one notification, and once you've got it, you're done. So having an auto-delete queue is pretty valuable there. As you create it, you use it once, you pull the message off of it, and you're done, right? And it just gets rid of itself. It's kind of like garbage collection at the broker level. So all of these are properties that can be assigned to the queue in any given. Okay? Questions? All right, now let's look at the simulator for a second. I should say, by the way, that this simulator is downloadable from various sources. The simulator, I'm going to show you the simulator in a second, but it was written by the guy who was one of the main developers for Rabbit. And he wrote it basically for this situation, so he could demonstrate network topologies, demonstrate messaging topologies in a classroom situation. It has one feature which is handy, which is that if you invent a topology inside this tool that we'll look at in a second, you can actually export it to a running version of Rabbit instead. Rabbit, like most messaging infrastructures, allows you to set up the topology in what amounts to compile time. In other words, the broker can read the topology from a bunch of XML files, figure out how to get itself organized, and create a bunch of queues and exchanges, and hook up the routing and stuff, all just as a side effect of launching itself. Which is an important ability in the real world, right? If a broker can crash and you want to bring the broker back up, you want to bring it back up into a known and useful state. By the same token, you can do all of that programmatically. You can create the entire topology just inside your program, but I don't honestly recommend that because it's not as robust, right? It's that everything has to work for that to work. as compared to having the topology just come up as a side effect. So one of the nice things then about this tool is that it gives you a visual tool for laying out a network topology that you can then export to Rabbit and then import into Rabbit. It's kind of cranky, is that the guy worked on it until he got it to the point where he was happy with it and then he kind of stopped working on it. But it is on GitHub, so you can download it and fork it if you want to. The tool, we'll look at it in a moment, it's built entirely in JavaScript, which is kind of interesting. So you can just run it. In other words, you can just download the thing and run it, which is what I'm going to do in a second. And it will also run under Node. So if you're going to do importing and exporting, you've got to run it under Node. And I'll give you the examples for how to do that there. Node, if you haven't used Node.js, it's basically a JavaScript, a server-side JavaScript implementation that has kind of a web server toolkit built into it. So people can build web servers, custom web servers using Node.js. And it's popular in the San Francisco area right now amongst the startups. There's a lot of people are moving over to Node for their web servers. It works pretty well. I'm not a huge fan of it because I'm not a huge fan of server-side JavaScript. It's just too hard to debug for me to be happy. So I'm still using Apache and Tomcat and things like that. I should say there's going to be a disconnect, a little bit of a disconnect between me and most, at least many of you guys, in that Microsoft technology has almost no footprint in the San Francisco area. I know of no startups that are using Microsoft technology for what they're doing. None. Zero. In fact, I know of no new Microsoft projects that are starting, except in shops that are already established Microsoft shops. I don't know anybody who's adopting the technology. So that's a cultural difference between the culture in Europe with respect to infrastructure. The infrastructure that's happening in the Bay Area is Microsoft is dying in the Bay Area, and it's still quite alive and healthy here in Europe. So I tend to not talk too much about Microsoft alternatives because I don't use them on a day-to-day basis. So I tend to not think about them. But if you have questions about some Microsoft thing that's equivalent to what I do talk about, just ask me. But this stuff does run on all Microsoft technology just fine. But anyway, nobody's using IIS in the Bay Area. It's almost all of the projects I know are either based on the web servers, either Node or they're Apache. And then there's a few other kind of little web servers that people use here and there when they need particular efficiency, but almost all of it's just Apache based. And then I put it up on my website if you want to fool around. So it's up there live right now. You can just go to that URL and it'll be in the zip. This one won't export, obviously, because it's sitting on my website. There would be no point in allowing an export to my local server. Okay, so let us look at it for a moment. Look at a couple of examples here. So I've put slides up here for the examples I'm about to give you, so that you've got some record of them. I get really annoyed when I go to sessions and somebody starts typing because I don't have a copy of any of that. It's not in the slides. It drives me crazy. Right? So I'm not a big fan of people doing live demos. It just seems to me to be a waste of time, and you don't have a record of it, so you can't take notes or anything. And it's not very useful. So I put copies of what I'm about to do in the simulator up here so that you can duplicate yourself if you want to fool around. But let's get out of PowerPoint for a second. Go over the simulator I have downloaded. So this is very simple in the way it's put together. It doesn't have we'll see in a moment that I can take a producer and I can drag it over here, and I now have a producer there. It is completely, it exists now forever. This tool has no means of deleting things. So the only way that I can delete something is I can come up here and hit the refresh button, and I go back to nothing, right? So those are my only alternatives to this tool. Is either all or nothing. We can have a basic system where I have a producer of a message, a consumer of a message. Notice that these have names. If I click on them, I can give the properties. So let's say that this is actually a logger consumer. Here, I can give it a name. And that's important in terms of general topologies, is that you want you access things by name, and a name like sim.gen-lte3nzg, and that's not a very useful name. You want a name that says something useful. So this one over here, for example, could be a web application. In between that, we have to put an exchange and a queue. You always have to have at least one exchange and one queue. And as I said, if you don't specify an exchange in your code, you're going to get a default exchange. Now, in order to do anything, we have to add some bindings here because these things are just sitting in outer space. So the first order of business then is that I've got to make a connection between my web application and the exchange, because that's how the routing is going to happen. Is that you never talk directly to queues, you always talk to exchanges. And then I have to make a connection between a queue and an exchange, so the exchange has some place to send the message once it gets it. There's no durability in the sense of holding on to messages associated with the exchange itself. Is that the messages can sit in the queues indefinitely. Now I can send a message at this point. So for example, I can just send an arbitrary message, and it just sits there in that queue. Notice that messages count is gradually incrementing as the message goes across the system and arrives in the queue, because there isn't a consumer yet. So I can add a consumer. Oops. It's picky about which direction you drag the arrows. And notice that as soon as I add the consumer, all the messages that were in the queue get pulled out by the consumer. So messages can sit in those queues indefinitely. If the queue is durable, it will even survive the broker going down and coming back up again. All right, so that's the basic message flow. Now, there are lots of ways that we can do this. I've called this one a logger. Let's set up another simple situation where I want to have some background processing happening. Let's say that my web application here is submitting images to the system, and I need to do some kind of processing on the image and then serve it back up to the web application, something like that. And processing is going to take time. I don't want to be using up machine cycles on my web server for processing images. Again, that's something that I see wrong in a lot of web applications that I look at when I come into a place as a consultant and look at the code. Is people do everything on the web server, and that's really not a good idea. Because the web server should be doing nothing but servicing the web pages as quickly as it possibly can. So if I want to do something in the background, well, I can do that pretty easily. I can add what amounts to a background processor. So let's put another queue on here. This is going to be the place where I'm going to send the images for background processing. Now, when the image arrives at this exchange, I do want to log the fact that it's arrived, but I also want to send it down to background processing. So I can take this second queue and hook it up to the same exchange. So everyone with me here? Now, the default behavior for an exchange is that there are several behaviors here. Notice there's direct, there's fan out, and there is topic exchanges. Now, fan out is probably the best solution here. So what fan out means is that every message that arrives on the input side fans out to all of the bindings on the output side, which is what I really want in this situation. Is everyone following what I'm saying? So I can now add some consumers over here. And since this is long-term background processing, I'll say, oh, well, it's going to take a long time, so I'll put three over here. And then hook them all up to the same queue. All right, now when I send a message out, going over to the producer to send messages, see how it goes? Now notice that the message here went to the block, the same message also was routed down here to this particular consumer. Notice what happens the next time I send a message. It's also going to go to the blocker, but now it goes to the second consumer. Third time I send a message, it goes to the third consumer. And then if I send a bunch of them, they will route to the consumer. So I'm getting a kind of load balancing here. Right? It's not perfect with a sense of load balancing. In other words, the decision about routing is not made based on how busy the consumer is. But it's not bad. Right? It's for most of the applications that you're going to be using messaging for, it works pretty well. So everyone look here.
So is that a competing consumer model that you set up, or is that just regular load balancing?
Well, it's load balancing in the sense of a round robin load balancing.
Okay, so that's the default behavior is round robin.
It's round robin, but it's not really a load balancer, right? Is you can't load balance based on the queue size, for example, because there's only one queue here, right? This is on the output side of the queue.
Okay.
Right? Does everyone see what I'm trying to get at? In other words, if we're talking load balancing at the web level, the decision about where to route the HTTP request is made with a whole lot of criteria. The most important of which is how busy is the server on the other side. And we don't really have a notion of busyness here. So we can't really consider busyness with respect to how this simple load balancing was working. Now, we'll see in a moment that we can control routing to a large extent. So we could actually write what amounts to a load balancer that would be using routing for doing that. But that would have to be code that we'll write. Just table the question for a minute. We'll see how to do it.
So is the consumer blocking? So if
The consumer is blocking, yeah.
okay, so if say one of them was taking 10 minutes for each message,
Yeah.
is there a way to throttle the messages on the queue so that they don't build up?
Well, the consumer's blocking, but that's just one thread on the consumer that's blocking. It's not the whole computer. Right? You could have what amounted to multiple threads pulling messages off the queue. You see what I'm saying? In other words, what's really happening on the consumer is just it's sitting in a loop, waiting for a message to arrive. Right? And when it gets the message, it could spawn off a thread for processing the message and then just go right back to waiting. Or not. It depends on how you want to do it, right?
Is there a way to prevent the queue for filling up to say 10,000 messages? Do you have any control of that?
No, but you can at least monitor it.
Okay.
And you can at least because if that's happening, there's something wrong. Right? That's a bug. And certainly the control panel for the broker shows you all of the activities on all of the queues that's the word, on all the queues, and you can see where the bottlenecks are. You can see the things you're getting stuck and you don't expect them to be. And then you can throw some additional consumers on that and find a bug in the consumer and fix it.
Are the messages always pushed to the consumer, or can they pull?
Well, the messages are pushed to a queue, but the consumer always pulls from the queue.
Consumer, right? Okay, so it's the consumer that drives that. It's not the queue.
So the
queue
consumer
doesn't
drives
push
it.
it. Yeah.
Yes, the queue just accumulates messages.
Okay, so the consumer will pull a message when it's ready to.
When it's ready.
Okay.
So the round robin is only happening because you've got multiple consumers that are waiting for a message.
In this case, yeah.
If they're all
But
busy,
this-
it would go to the first one that came through.
Right. All right, and this exchange is again a fan out exchange here. So so not like these. That's fine. But you saw me set it as a fan out exchange a moment ago, and that means that it's going to go out to everything. Right? There are other kinds of exchanges which are also important. As I was going to demonstrate here, but it's not going to change the queue property. I'll just do another example in a second.
Another small question. Would you name all these elements?
Yes.
And is there a best practice for doing that? Or?
No. Well, we'll see that there's not so much a best practice, but there's a kind of dotted notation, A.B.C.D, that you have to use in order to do routing. And we're not quite there yet in terms of demonstration. Other than that, just naming something that's sensible. You know, you don't, strictly speaking, have to name everything because sometimes you don't care. But I like to name everything. It makes everything easier to debug when things have decent names associated. So even if I'm not using the name of the program for anything, I'll use it just so I can debug the system more easily. All right, and everything can be named, particularly the queues. It's important to name the queues because that's how you connect to a queue is by name. Okay, so we're okay so far. Now, if I can change this to direct, I would be utterly happy, but it's not letting me do it, so I will give you one more example here. Producer, let's change. I'm not going to bother with the concerns. This is, as I said, this is a cranky tool, right? What I just did is this one doesn't have anything connected to it, so now it's letting me change the distribution property, which is wacky. I ought to be able to do it anyway. But remember, I was using fan out earlier. Now I'm going to do it as a direct queue. So let's talk a little bit about bindings. I have a producer, which is hooked up to this direct queue, or direct exchange. And so messages are going to go to the direct exchange, and then I'm going to put a few queues on the outside. Okay, there are 3 binding keys here. I'm going to change their names. This one will be apples. And I'll make this one oranges. And I'll make this one oranges. And I'm not specifying anything here. All right, so everyone following what I've done so far. So if I go here and I put a routing key here of apples, it goes to apples. If I put a routing key here of oranges, it goes to both of the oranges. So that's my simplest routing strategy, the simplest use of bindings. There are more complicated ones which I will get to momentarily, but this is the simple. So the difference between a fan-out strategy and a direct strategy is that the routing key here in the direct strategy is used to control the output side of the exchange. And it just goes directly to whatever name matches the routing key on the message itself. Is everyone understanding how this is working? It's like a message type. And you can use this for a very simple post-up kind of situation. Right? It's as if these 2 queues are subscribing to the oranges publication.
So all the producers writing to that exchange need to know what message types are available.
Well, it needs to know what the bindings are. Yeah. So again, I don't want you to think about message types. I want you to think in terms of bindings, because that'll keep. You start thinking in terms of message types, there'll be eventually a metaphor mismatch there that'll make things more confusing. So think in terms of the bindings. Right? So the notion of an exchange which is put into direct mode is that it pays attention to the routing key. In fan-out mode, it paid no attention to the routing key at all. It just ignored it. Right? In direct mode, it actually pays attention to the routing key, and it will route the messages only to those outbound paths whose binding matches the routing key. And it has to be an exact match in this simple situation. All right, so everyone follow. So, let us look at a slightly more complicated situation. Here I have a producer, and I have an exchange. And this exchange I'm going to put into the 3rd mode of interest, which is the topic mode. So topic mode is, again, another mode that controls how the exchange routes messages from its input side to its output side. Now, the simplest possible situation here is I have get everything connected. All right, so my binding key here, I'm going to say this is some server and some application on that server. So that won't make it easier to type. And some something that I want the application to do. Log or something like that. So I now have what amounts to a 3-part binding. So everyone with me here. So if I go to send a message, if I specify the whole thing as the routing queue, it will. Oops, what did I forget?
What we want.
Oh, thank you. There.
What happens in the case that you get it wrong? What happens to the message?
Doesn't just disappears.
Right,
It's
okay.
just discarded. Okay, so it's everyone. So this is working much like direct mode would work, and I fully specify the route. I'm fully specifying things. But when I'm in topic mode, I have finer control than I have in direct mode, in that I can start using some wildcards. So let's put a couple of wildcard cues. So I'm going to bind this one to star.log. And I'm going to bind this one to star.app1.log. And I'm going to bind this one to star.app1.star. Okay.
Could you do just star?
That's a really good question. I've never done it. Let's see. I have oh, I need two of them. So I can just sit here and not do anything. I'm moving dangerously here. I have no idea how this is function, but we'll find out. So let's see. And so if I just send a random message here to server.app1.log, what's it going to do? It just goes where I tell it to, right? Is everyone following what I'm doing here, right? But what am I doing wrong? Server.app1.log. This should have gone to app1. This should have gone down to both of all of these actually. So what's wrong? What's the direct mode? Have that the topic mode. Let's try that again. Okay, that's what I want. Right. In other words, the output server1.app1.log is being accepted obviously by the exact match, but it's also being accepted by star.app1.star because that's a match. And it's being accepted by star.app1.log because that's a match. Well, it didn't go to star, so I guess star doesn't do anything. All right? So is everyone following me here? Is that if I go to foo over here and send it, it goes to star.app1.star because everything else wants something to the right of the dot, right? They want that dot log there, and there isn't a dot log. If I put dot log in, and I send to app2 rather than app1, it just disappears because I don't have any binding associated with app2.
So would you need to have star.star.log in order for it to go to that second one from the top?
There's a better way to do that, but let's try it. That'll probably work.
As a producer,
Yeah.
so as a producer, do I know that a message I've sent to the wrong routing has been discarded?
Well, I'll talk about this when I get to the code, assuming that we have time. I think I will. But there's an acknowledgement that comes back,
Okay.
and so you can guarantee that it arrived. In other words, it got somewhere.
It's got to the queue, or it's got to the consumer?
That it got to the consumer. You don't care whether it's in the queue or not. It's in the consumer.
So there was no consumers listening, and
But if they connect at some later time, then they'll suck the message out, and then you'll get the acknowledgement. Yes. Okay? So is everyone with me in terms of how this is working? There's one other option that we can put in here. Instead of star.log, I'm going to make this hashmark.log. So star connects to exactly one word. The way that we had to do it, when we said star.star.log, I said that'll probably work. It's because star represents a word. Hash represents 0 or more words. So as soon as I say hash.log there, Now anything that's got a .log at the end of it is going to end up there. Right, so star.log and hash.log are the same thing, basically.
So the period character is significant. You use other characters.
Those are the only two. Star and hash mark are the only two.
Only to separate words in a
Right, a dot is meaningful.
Right. It has to be a period.
It has to be a period. You don't have any option. All right, is everyone with me in terms of how this is working? So the issue here is that if we're talking about a publish-subscribe model, this gives us much finer control of what are called topics. Right? Is that when people talk about messaging traditionally, they would talk about queues and topics as separate things. Right? In a queue, you would send a message to a queue, and then you could pull it off a queue, or you could publish a topic, and then subscribers could receive messages on that topic. This does the same thing, but it does it in a somewhat more complicated, but also much more powerful way, because you can now have topics and subtopics and sub-subtopics effectively, and control how the routing happens based on the bindings, which is something you can't do with just a single topic. The single topic model is essentially the direct routing model. But when we go into topic mode, so-called topic mode, in the exchange, now we can have very fine control over where things are being routed. Okay, so is this starting to sink in? Is everybody understanding how this is working?
So this server app log thing is essentially arbitrary. You have as many dots in as you
as many dots as you want, and you can make the words anything you want. So it's completely arbitrary. And if you misspell it, you're host. So, so do the spelling with like short words that are easy to spell. I actually have no idea whether or not it's case sensitive. I've always done it with nothing but lowercase. Okay? Is everyone with me? All right, let me give you one more example because it's a common example, so it's worth looking at. Imagine that we were doing some kind of RPC thing. So here I have a producer that's going to an exchange, and I'm going to make this one a topic exchange. And there's a queue on the output side that's going to accept the messages. So this is not earth-shattering so far. And I'm going to make this binding just be a request. Imagine this is our RPC model. This request 1 is function 1. And I'll put in a few other RPC calls, remote procedure calls. So this one here can be request 2. Okay, is everyone following? So we're in topic mode, but I'm not going to bother with dots, so we may as well be in direct mode. But if I send out request 1, it's going to go to the request 1 queue. And if I send out request 2, it's going to go to the request 2 queue. So this is basically like making a remote procedure call. But what happens if I want to do things in a more complicated way? So let's say here I've got a one-to-one between the server and the requester. But let's say that there's some operation that I want to distribute between multiple places. Now there's several ways, several topologies that we've used to pull that off. But one of them is to put another exchange into the picture. Now this particular exchange, I'm going to make it as a direct exchange because that's all I need right now. And I'm going to connect it to the first exchange. And the binding here is going to be for request 3. And then on request 3, I can put a queue for the objects that are going to actually handle the request. All right, so let's put a couple of consumers on this one just to so I can demonstrate what I'm getting at here. Direct, so I'm going to make this a request. But let's say I also want to log requests for request 3. I'll put a queue for logging on as well. So this is the logger. This is the background, one of the background processors. And this is another background processor. Okay, so we're in with me with my binding. So let's send a message. This is request 3, and away it goes. Right? And I don't have a connection. So it went to the logger. Oops. But it also went to one of the 2 services. If I send another one out, it's going to go to the logger and the other of the 2 services. If I send a bunch of them out, then they're going to go to the logger and they'll be distributed amongst the services. All right, so it's going to get sequence. So this is an exchange to exchange communication.
So how do you send a response back?
Again, we'll look at some code in a moment, but basically one of the fields in the message header is the name of the queue into which the response is expected. So the receiver of the message then is responsible for publishing a response, but it's publishing it to a very specific queue, which is the queue that the producer of the request is waiting on. And there's a second piece of information in the header which is equally important, which is typically a unique number. If you were programming C#, it would be a GUID that identifies this specific message. So that way, if a particular producer sends out 5 identical messages, it can give them each unique identifiers. And it will get 5 responses back, but then it can then use that identifier to match the particular response to the particular request. All right, so that information is carried in the message header, though.
Is that done by default by Rabbit?
No, you have to set it up. There's a couple of method calls that you use there's an argument. When you set up the message, you can pass it parameters. And one of the fields in the parameter object is the ID, and one of the fields in the parameter object is the name of the response queue. So typically, if you are going to, in an RPC model, the caller has to have a response queue to receive the return value, basically. And in an RPC model, the receiver has to get the request, do the work, and then issue a message to the response queue with the result as its payload.
How does it route, sorry, how does it route the response back? Does it go back to the broker?
Well, it goes into the cloud effectively. In other words, it's just, the response back is just a message.
Yeah, but so you said it like you specify a queue.
Right. So if I was going to put it back, I'd have to put a queue here to handle responses.
Yeah, but how do you get to that queue?
You just have to add it. So there's essentially this object over here is both a producer and a consumer in that case, and it will have a queue associated with itself, right? And this will be a named queue. So this is the response goes here queue. So there's my response queue. And then this, not the logger, but let's say one of these background processors would then also effectively be a producer, right? Because it's producing responses. So is everyone following what I'm saying here? And then there'd be an exchange. You can start seeing why I went to picture. It gets crazy after a while. Right? But so here I've got my connection to the response.
So it always has to go through an exchange. You can't
Yeah,
just...
everything has to go through an exchange. Right, so this guy, background 2 here, gets the request. The request carried with it the name response. Right, it's really binding, right? So there's got to be a response binding along here is the binding key. Right, is everyone following me here? And what it would do then is issue a message to using the response binding, which would eventually arrive in this queue, and then the producer would get it. Right, now what would be carried along this path is the unique GUID, if you will, of the request, so that if this guy, if this response queue has 6 responses sitting in it, this guy has to be able to match the response with the original request, to match the return value with the original call. So it's going to use that GUID that's part of the message header to make that connection.
Do you mind repeating why we need the additional exchange? The second one?
Yeah, what's the benefit of the second exchange on the request? Then just
Well, because you can't.
you have it used directly to the.
You could use the anonymous exchange there, but there's only one anonymous exchange. Right? In other words, you always have to have an exchange. This is just the model. There always must be an exchange. So you can't send something directly to a queue. You send things to exchanges. And if you don't specify an exchange, it all goes through this default nameless fan-out exchange. And in practice, that's not a great strategy. First of all, it would get overloaded, and secondly, it doesn't really fit into your routing scheme very well. So you can never have a queue standing by itself, though. Every queue has to have at least one exchange associated with it. Now, there could be multiple exchanges. In other words, I could have repurposed the existing exchange to handle responses, and then use topic routing in order to make sure that if it was a response, right? So I could have, in other words, I could have the binding could be function 1 and then function 1.response, or function 1.request and function 1.response, and then I could use the topic routing to route the response down to one queue and have the request go to the other, and then I could get by with a single exchange that's handling both the request and the response. So that would be fine.
So you can't have multiple queues with the same binding. Is that why you add?
Well, the binding is the relationship between the queue and the exchange, really. So you can have multiple queues with the same binding. And
what would happen if you do that in this case?
Well, I kind of did that here, right? Is that here I've got 2 queues that are both bound to request, right?
But why? I still don't get why you need that second exchange here.
I was trying to make it simpler. So I could, for example, have a queue, a producer here that's going to handle the response, that would then be bound. This is going to get too complicated very quickly in terms of the picture, to this exchange.
Okay.
Right, and then this binding could be request to. Right, and I don't, and then this binding would have to be request 3. Is it letting me change it? What's going on here? Is it not letting me change the binding? Well, you get the idea, right? If this binding was request 3.response, and this binding was request 3.request, and when I send a message that has a routing queue of request 3.request into this exchange from here, it will go to the request. And if I send a message with the binding request 3.response into this exchange from here, it'll go down to this response queue. Is that making sense?
Don't you have to set up a binding for that to work?
Well, there'd have to be a binding here, right? I'd have to have a. This is getting too complicated. If I'd have to have a binding here that was. This would be request 3 response, and this one, right? That's going to have to do. Oh, I don't have a queue that's. Right. Oh, that's interesting. That's why it's not working. Is you can't hook up producers directly to. No, you can hook up a producer exchange. What do I do? So it should.
You don't need a binding on that.
Oh, I don't need a binding because it's a 1-to-1. Yeah, thanks. Right, the problem is that this is still not going to let me change it, but this is, remember, was a direct queue. Is that in order for this to work, this would have to be a topic queue, and it's not, or topic exchange, it's not. So that's not bad.
Is there any overhead with having multiple exchanges?
Well, some, right? It's always a data structure. But I'd be perfectly happy to accept a single exchange that handles everything associated with request 1, both the response and the request. I don't see anything at all wrong with that. I was trying to simplify by putting a separate exchange in, but clearly I was misguided in my thinking here, right?
Two-part question. The first part, is it correct that the exchange and the queues reside in Rabbit? You said that.
The exchange and the queues both reside inside the broker, yes.
Yes, okay. And wouldn't it make sense to have the first producer and the response consumer in the same code or in the same app, so you've got it, have it together?
Well, they will be, yeah, absolutely.
You could
In other words, if I'm doing a procedure call kind of thing, I'm going to make a class that handles both the consuming of the request and the transmission of the response all in one class.
Yeah, but it's just...
And so it's all going to be on one machine.
Why would you use these over JMS? Is there?
It's just more flexible.
Okay.
It's this is obviously not JMX, right? We look at it has its own API.
Yes.
But I like it better. I used JMS for years. I have to say that I could never find an open source JMS implementation that I was ecstatic about, because they're all buggy and weird. And I have spent more of my life wrestling with Tortoise than I care to discuss, right? And I just got fed up with the whole thing. And I haven't had those problems with Rabbit, which is not to say that they don't exist. It might just be that my use cases are not the ones that uncover the bugs. But so far, I've been pretty happy with Rabbit in terms of reliability and ease of use. So once you get used to this way of thinking, it's actually pretty powerful. Particularly being able to have topics and subtopics and sub-subtopics. That's actually kind of nice, because you can like hook logs in places where you want them. You can do it dynamically, right? As I said, this can all be loaded into Rabbit as part of its configuration, but you can also do everything here dynamically with method calls as your program is running. So I can create a queue for logging purposes at runtime when I'm debugging, just to see what's going on. And then when I'm done, I can just eliminate that code and the queue's not there. It's not cluttering up the system anymore. That's kind of handy, actually. The JMS implementations that I've worked with, almost all of the messaging topology had to be done at configuration time. I had to set up the topics at configuration time. So I like having the option of being able to effectively configure at runtime. It's kind of handy.
Plus it's free. It's free. So.
It's free, yeah. Free is good, yeah. With JMS, the only system that I was happy with was one called RabbitMQ, which was expensive. It was the opposite of free. It was quite reliable, but it was very expensive.
How about the service bus?
How about?
And service bus. And did you use it?
I still didn't do.
And service bus.
He's asking about service bus.
I haven't used it.
It's
very slow.
I can't help.
I seem to remember a fourth topic exchange, or I never use it. I've never pressed it at all.
There is a fourth type of exchange, and I have never used it, and I don't even remember what it's called.
Header exchange. Header exchange.
Header exchange, yeah. Have you used it? Do you have any idea?
It's based on the message headers.
Just on the message header, yeah. But I'm for what I do, which is mostly RPC kinds of stuff and pub sub stuff. I've never needed to use it.
Do you recommend the RPC? Because on the web page they put a warning label on the RPC.
It's arguable. The reason people don't like RPC is because you send the request off and it may or may not get serviced, and you don't know how long it's going to take to get serviced. So it's kind of hard to guarantee response times if you're sending requests off and you don't know what's going to happen. The downside, of course, though, is that if you're not using RPC, you're doing the processing locally, so you're using up machine cycles locally. So I use it a lot when I want to have remote objects, when I want to have distributed process.
So you would recommend?
I would recommend it, but I bear in mind that that's somewhat controversial, because there are people that would certainly argue with me about it. Now, the reason that I do this is because architecturally, when I build my systems, what I like to have is each module being a standalone system with a well-defined API to it. And being an OO kind of guy, I tend to define my APIs as sets of message calls, or RPCs in other words. So I like doing that for several reasons, the most important of which is that it makes test-driven development much easier if you're using an RPC-style API, because that gives you an interface that you can mock inside your TDD framework. Right? So when I do my initial development, I'll have a Java or a C# interface, and then I'll mock it using whatever, mock with a Q if I'm in C# land, and JMock if I'm in Java land, and get everything working, right? Make sure that I have the interface correct. That's the whole TDD thing. It's all about design. It's not really about testing. It's about designing the interfaces. And then when I get it working, I'll implement the thing to send a message. Right, see what I'm saying? So when I'm test mode, I'm making a direct connection locally, but then I can just insert the messaging system in the middle of that, and it's completely transparent to the client and the producer of the receiver of the message itself. Right, so that way I have both options in a sense, is that I can plug messaging into it if I want to, or I can plug messaging when I'm testing. So I do it for architectural reasons. And the downside is that I do have to pay attention to how long it's taking for messages to be processed and do something about it if it's taking too long. So it makes the code a little more complicated because you've got to manually do that.
The exchanges, do they just pass messages? They can't
Yes.
do any transformation on messages?
They don't do any transformation at all.
So if you want to do partition a database search across 3 workers, you would have to either split that into 3 messages on the producer, or route it to something that splits it.
Well, or have 3 consumers that attach the same queue, any of those.
Yeah, but if you wanted to say the first one, look in volume 1 on the database, second one, look in volume 2, because you're doing a search. So
Yeah, but you see, you could do that by having a fan out to 3 workers,
yeah.
each of which handled its piece of the database,
Yeah.
right? Each volume, and then the one that found it generates the response and posts the response. The other 2 just throw the request away. You could even do kind of a poor man's MapReduce if you wanted to,
Yeah.
because they could all return responses, which you could then filter out of some consumer someplace.
So would you use the header exchange type model for handling something like that? The producer would say, I'm looking for a whatever, and then the exchange would know based on the headers to send that to worker 1, which is responsible for that partition?
I guess you could, but you could do the same thing with topics. So there's always multiple ways to do everything. But yeah, I guess so. I'm kind of nervous here because I don't have direct experience working with the header style exchange, so I don't want to say anything wrong. But based on my limited understanding, yeah, it would work.
So the messages that go around, they're not, well, they could be XML or JSON, but
Anything, it's just a
they're
binary
binary.
blob, yeah.
So they should be quite efficient in terms of space on the
Yeah.
wire.
Yeah. And the more often than not, when I'm doing RPC kinds of things, I convert it to JSON just because it makes it easier to debug when it's all strings. But there's no reason to do that. I could be sending binary across. Now, bear in mind that if you are sending binary across, if it's like numeric data, you're losing a lot of the advantages of doing messaging, right? Because an integer is represented in different ways on different platforms, and sending an integer across, God knows what your receiver is going to be able to do with that, unless it's in the same language running under the same platform as the producer. So I almost always convert to JSON and then convert back out again on the other side, just because that gives me some interoperability between platforms that I wouldn't have if it was actually binary.
Is there any size limit on messages? Because you were saying earlier about if you're processing images.
Again, I'm sure there's a practical one based on.
Would you send the images as the message, or would you just send basically a pointer to?
I send the image. I would send many images. Messaging systems, you just send the whole image across. But again, bear in mind that if everything's durable, you're taking all that data and storing it on a disk, right? So it's going to be taking up disk space, and it's going to take more time to send the message because the message has to be staged to the disk.
So it basically just depends. Smallish, you'd be all right as long as it's not going to be a flood of.
Well, even if it's long though, if you've got to send an image, you've got to send an image. So you might as well send it in binary because it's going to take fewer bytes on the bus. Right, and there the binary formats are well defined anyway, so it doesn't matter what the receiver platform is.
I was just thinking alternatively you could sort of upload it to a blob storage somewhere.
No. See, that's exactly what I don't want to do.
Right.
When I was saying earlier, don't use databases as a way of transmitting data, that's exactly the use case that I have in mind when people do that. They'll take an image and they'll load it to a blob store, and then they'll send a key across some message, and then they'll use that key to look it up from the blob stores. Don't do that. Just send it in the message. It's much more efficient.
Well, the thing is, if you start putting the message, you've got a sort of 300 meg picture going through, or 300 meg API file. Your message system stalls for a couple of seconds whilst it's transmitting that message.
I can't.
If you're transmitting a 300 meg API file through your messaging system, your messaging system is going to stall for 2 or 3 seconds whilst it's transmitting that message.
Well, it could, right? So, which is why you'd have a relatively large cluster inside the broker if you were regular sending huge things through it. Absolutely. Right, but bear in mind it's not single threaded. The broker is not single threaded, so it's not going to stall. It will slow down though.
Yes, but even so, you're putting a very large message.
You're putting a lot of load on it.
Which is
Yes.
just going to.
Yes, you're putting a lot of load on it. But you're putting less load on the system overall than you would put if you were using a database. Because the database is going to load the CPU also. It's just a question of which CPU are we loading. Are we going to load the one that's in the broker cluster, or are we going to load the one that's in the database cluster? Right.
You
So
use an Amazon
the
S3.
load is going to happen. But
You could use Amazon S3 for that. There's no reason to put it through a database.
you could.
Yeah,
And I do.
that's what I was thinking of.
So you could, sure. You know, again, it all depends on topology. It depends on what you're trying to accomplish. And yeah, I use S3 for images usually.
Can you send the cross-domain messages to the other domain and read as well?
Well, again, the message payload is an arbitrary binary blob. So it's up to you to make sure that you're sending things across domains that's going to be readable on both sides. Right? And the one least common denominator thing to send is something like JSON that's ASCII, right? That's understandable and is interpretable on both sides into whatever makes sense binary, in a binary. And again, you get back to images, and the image itself is a binary thing, but it's a well-defined standard that is understood on both sides, so you're okay sending binary there. But I wouldn't send an object through the system in binary. I wouldn't use Java serialization, for example, to send an object around like a messaging system, because that locks me into Java on the consumer and the producer.
If I send a huge amount of data to a broker, will it increase performance if I increase the number of exchanges and queues?
No, because it's all in the same program. What would increase performance is putting more CPUs into the broker cluster. Right? It's all machine cycles. Ultimately, it's all machine cycles.
Are there any sort of inbuilt security or encryption?
SSL supports SSL for encryption. So if the broker is physically distributed, you can set up the bindings between broker instances as SSL connections, and you'll get SSL across. But that's all that you
Is
have.
that the same for the original sort of producer sent message at the two ends of the process as well?
Well, you can make the tunnels secure. You can't,
Yeah.
right? It's not doing anything else. If you want to encrypt the message, that's how you get real security.
Yeah.
Right. So if you were sending credit cards around, I'd probably encrypt them. But at least you get end-to-end SSL between the producer and the consumer if you set it like that.
So it supports different types of transport.
Well, it supports TCP transport. I don't know if they might use UDP. I don't know. It's not something that you have to worry about, so I've never really given it a lot of thought.
I was wondering whether you can go through WebSocket.
Some of the clients, the Rabbit itself doesn't come with a client that uses WebSockets, but there are WebSocket clients that work with Rabbit. So you can actually have a JSON application that is running locally in JavaScript using WebSockets to talk as a producer or a consumer using WebSockets to talk to the system. But that's not part of the Rabbit project itself. It's a separate side project.
What if I'm sending a huge chunk of data from my, let's say, queue to consumer, and the network goes down?
If it's durable messages, you're okay.
Also, in the middle of the transfer.
Well, I'll refer you to the documentation. There are a couple of use cases or app use cases or however we're going to call them that are called out specifically in the documentation. The short answer is you won't get the app. So there's an acknowledgement that you can set up, right? It's not default. So there's a field that you set and you send the message that says I want an acknowledgement. And if you don't get the acknowledgement, you just assume that it never arrived and you send it again. There's no timeout in Rabbit. So if there was a time, if you're waiting if you want a timeout, you want to say, I want to get the ACK in a minute.
Yeah,
right, you have to do that yourself.
I was thinking if someone trips over the router or something.
Yeah. Okay? So we're actually running over. This is what I really wanted to do in this session, so I'm happy. The rest of the slides, I was basically just going through the tutorial that's up on the Rabbit website. And I recommend that you do that. It's a good tutorial. You'll see that when you work through the tutorial, most of the common use cases are represented. in 5 different languages. So you can see the same example in Java and C# and Ruby and Python and whatever else they've got up there. I don't remember offhand. But just to get a feel for what it looks like to be implementing in different platforms. He's done it all in languages. So this is the important part, though, because this is the part that's hard to understand. And you'll see in the examples in the tutorials that basically all that they're doing is setting up the exchanges and the queues exactly what they do graphically here, except they're making method calls to do that. And then putting a message into the system and it flows through. So this is the conceptual issue. Okay, so I will stay here if you have additional questions, but I'll let the rest of you go. And if you get a moment, please do the evaluation inside.